Hey everyone, this is Vishal and I'm a student from the first batch of Abhiyanan Super 30 and I'm currently a BTech 4th year student in IT Roorkee. So today for this lecture we'll be covering functional equations, and functional equations are basically equations in functions. So say for example we had a traditional variable called x, and in these kinds of equations we replace x with fx. So you get the general idea. Say for example we had a equation, say x plus 3 is equal to 3 into x. So if this was supposed to be a functional equation, it would be fx plus 3 is equal to 3 into fx. And the solution for this is pretty simple. Fx would be a constant function which is 3 by 2. But the thing is, functional equations aren't that simple because this is a pretty advanced topic. So I'll be showing you an example of a simple functional equation again, but it's on a higher level than this. Functional equations generally are solved by substitution. So say for example we have a functional equation called fx plus 3 is equal to x square plus 2x. So what are we going to do into this? How are we going to solve this equation? So the first thing that would occur to you is to replace this x plus 3 by new variable y. So it becomes function of y is equal to y minus 3 plus square plus 2 into y minus 3, and y is equal to x plus 3. So yeah, you get the general idea how this is going to be solved. You simplify this and you get the answer. So that's pretty simple, but things don't end so simply. So we'll be covering a very simple method to solve functional equations, and that is the principle of mathematical induction. Okay, so functional equations are also solved by principle of mathematical induction, which states that if a statement is true for a natural number k, and it is also true for the natural number k plus 1. Also, there's one more if condition, that the statement is also true for the number 1, or for any other number, for instance. So we can safely assume that the statement is true for all natural numbers, and we'll use this to solve many kinds of functional equations, and the first question we'll be covering would be based on this. Okay, so the first question we'll be covering is from the book Excursion in Mathematics, and we'll be following exclusively this book for all the topics. So yeah, one thing I forgot to mention previously is that for you to learn functional equations, you should have a good grasp over mathematical induction, polynomials, and other stuff. So let's get started. The first question is to find all the polynomials px such that p of fx, where fx is a function, is equal to f of px, and p0 is equal to 0, and fx is a function which supports fx is greater than x for all x greater than equal to 0. Yeah, so we'll be following mathematical induction to find the answer for this question, and the first thing we're going to do is assume x is equal to 0. So it's the obvious choice. So yeah, here's how we proceed. We put in f x, which is 0, is equal to a naught. We just assume one value. Then we put it into the equation given in the question, which is p of fx is equal to f of px. So p of f of 0 is equal to f of p of 0. Yeah, but now we know that f of 0 is a naught. So p0 becomes a naught here, and f of 0 becomes a naught here. Hence what we get is p of a naught is equal to a naught. Now what we'll do is we'll assume f of a0 is equal to a1, and we'll put the same thing back here. And when we do that, we'll find out that p of a1 is equal to a1. Yeah. Now one more thing, since it is mentioned that fx is greater than x, that means a1 must be greater than a0, which is definitely greater than 0. So yeah, that means we can continue this further to infinite. Basically we can put in any number k and we can go there. Also, we have not put any restrictions on a0, a1, on what they are, whether they are natural, rational, anything. So this statement holds true for every other number. Yeah, so by this we can derive that px is equal to x, because the solution px minus x has infinite roots, hence px must be equal to x. So yeah, that's the solution of the question, and that's how we solve the first question. Okay, so here is the second example, and yeah, the examples are going to gradually escalate. So this is the second question and I'll read it out to you. Prove that fn is equal to 1 minus n is the only integer valued function defined on integers such that f of fn is equal to n, where n belongs to integers, f of n plus 2 is equal to n, where n belongs to integers again, and f of 0 is equal to 1. So now looking at this question, how are we going to solve this? So the first thing we see is that this is kind of a recursive function which is coming into picture. So we need to replace this recursive function with the first level of the function, that is just fn. So how are we going to do that? I'll just show you. Let's write the first statement in somewhat other fashion. F of k is equal to k, where k belongs to integers. So it looks like I have made no changes, and you'll see why this is important. Then what we do is we replace the we write this function, this statement here, f of n plus 2 as k, because this is also going to be an integer, and we can safely assume it to be another integer k. So yeah, the statement now becomes f of k is equal to n. So now what are we going to do with this? We operate with a f on both sides. Well, it's not operating, it's just you pass it to the function, and what we are going to do is, since functions have definite value for every input that we give, hence we can safely write this down. f of k is equal to f of n. Now what did we just write here? Like with this equation we can easily replace this with k. So what this becomes now is k is equal to fn, which is equal to f of n plus 2, which is what we assumed earlier. So finally it becomes f of n is equal to, f of n plus 2 is equal to f of n minus 2. Hence this is decreasing. Yeah, right? Now what are two types of integers? They are even and odd. So we'll put all of these types of integers into this and check it out. So let's start with even. Since one more statement is given here, we'll need to use this statement. So first of all, we'll put in the even integers. So let's put in n is equal to 0 first. So f of 2 is equal to f of 2 is equal to f of 0 minus 2. And again we put in n is equal to 2, which makes it f of 4 is equal to f of 2 minus 2. Now we already know what f of 2 is, so we can just replace it here and this becomes f of 0 minus 4. So we see a pattern emerging when we continue to do this, and the pattern is f of n is equal to f of 0 minus n. This is for even ones, right? Now what happens if we do for the odd ones? Let's put in 1. F of 1 plus 2 becomes 3 is equal to f of 1 minus 2. So this means again when we put n is equal to 3 here, then we find f of 5 is equal to f of 3 minus 2, which is f of 1 minus 4. Yeah. Now again we can see a pattern emerging here, and the pattern here is f of 5 is equal to f of 1 minus 1 plus 5, or the pattern is finally f of n is equal to f of 1 minus 1 plus n, right? Yeah. So this is for the odd ones. Okay, so now we have these both equations. Oh, wait a second. Yeah, so we now have these both equations for the even and for the odd. So now we need to find f0, which is already given. We need to find f1. So to find f1, we'll just chuck it into this equation here, which becomes f of 0 is equal to 0. That means f of 0 is 1, hence f of 1 is equal to 0, right? Now we know f of 0 and f of 1. So for even it becomes f of n is equal to 1 minus n, and for odd it becomes f of n is equal to f of 1, which is 0, minus 1, just a second, this is minus over here, I'm sorry, plus n, minus n. Yeah, right? Yeah, sorry for the mistakes here. Hence 1 minus n. So it is consistent with the both even ones and the odd ones. Hence for all integers n belong to z, we can write that fn is equal to 1 minus n. And that proves the question. Okay, so now we're on the third example, and the example is pretty simple, but it kind of highlights the smart ways of dealing with functional equations. So the example is, determine all functions on the real domain such that fx into fy minus fxy is equal to x plus y. So it works in two variables, which makes it even easier. So the first thing that occurs to you is to put 0 somewhere, and let's put y is equal to 0 arbitrarily, because this equation is kind of similar in x and y. So we'll just put y is equal to 0 here, which makes the equation fx into f of 0 minus f of 0 is equal to x plus 0, which upon simplification gives f of 0 into fx minus f of 0 minus x is equal to 0. Now say for example we put x is equal to 0, and 0 is on the real domain, so we can put everything we like. So the equation would become f of 0 square minus f of 0 is equal to 0, which means it has two roots. So f of 0 could either be 1 or f of 0 could either be 0. So now we are going to check both of these in this equation here. So let's put in f of 0 first. F of 0 is equal to 0 in first. So if we put f of 0 is equal to 0 here, the equation would give fx into 0 minus 0 minus x is equal to 0. Hence x is equal to 0. But x belongs to the complete real domain. So this is a contradiction here. Hence we have to rule out this case. Hence f of 0 will be 1, and we'll use this to find out fx. So here's how we are going to do that. We'll simply just put in f of 0 is equal to 1, which means fx minus 1 minus x is equal to 0, which means f of x is equal to x plus 1 for all real domains. Very simple, huh? Okay, so here we are on the second last example, and we are going to cover a pretty intensive question, algebraically intensive. So here's the question. We'll start. If function on the real domain satisfies the three given conditions, that is f of minus x is equal to minus fx. The second condition is f of x plus 1 is equal to f of x plus 1. And the third condition is f of 1 by x is equal to f of x divided by x square. Then we have to prove that f of x is equal to x for all x in the real domain. So that kind of seems pretty easy to guess. You know, f of x would be the only function to satisfy, but how are we supposed to ever prove it? So let's dive into it. The first thing we'll do is we'll need to find a correlation between the three given equations. So we'll just substitute the third equation into the second one, and for this we'll replace x by 1 by x. So the second equation would become 1 by f of 1 by x plus 1 is equal to f of 1 by x plus 1. So now what we'll do is we'll again substitute the third into this equation. Hence this is going to become f of x by x square, correct? And yeah, so you'll just know where we are getting with this. F of x by x square plus 1. So since we could have gone some other route as well, but this kind of seemed like a safe route because we can directly find out fx. So all we need to do is we have sorted out the right hand side. We just need to sort out the left hand side here, which is f of 1 plus x by x, and this would lead to f of x by x square plus 1. So now how are we going to satisfy the left hand side? Like, how are we going to simplify it into fx? So we'll again use the third identity here. So let's say f of x plus 1 by x is equal to f of say this is 1 by x, which is we could write it as 1 by x plus 1, and this would translate to f of x divided by x plus 1 ka whole square, which would lead to x plus 1 by x ka whole square again, a whole square again, into f of x by x plus 1, correct? Now we are left with this. Now since we've separated out the x over here, now we are left with this. So what is this thing? This is basically f of 1 minus x by x plus 1. 1 minus 1 by x plus 1. excuse me for that. Yeah. Now we can use the second identity here to simplify it to f of 1 minus 1 by x plus 1 is equal to f of minus 1 by x plus 1 plus 1, right? Hence finally the LHS becomes f of x plus 1 by x is equal to x plus 1 by x ka whole square into 1 plus f of minus 1 by x plus 1. There are no errors here. Now we can use the first identity here to kind of transform this into f of 1 by x plus 1. So when we do that, we'll get 1 plus, in the brackets, just in the square brackets, we'll get f of this would be replaced by minus sign here, and 1 by x plus 1. Yeah. Then we'll again use the third identity over here to kind of make the equation look like this. This is in the form of 1 by x, so we'll just put this f of x plus 1 divided by x plus 1 ka whole square. Yes, and now we're getting there. Now we know the second equation would fit right in, and it would make it f of x plus 1. Hence we can finally write down this equation as f of x plus 1 by x is equal to x plus 1 by x ka whole square, square brackets, 1 minus fx plus 1 by x plus 1 ka whole square. Yeah. So what we'll need to do is we'll need to put this right here, and we'll just get there. That is f of x by x square plus 1 is equal to x plus 1 by x ka whole square into 1 minus fx plus 1 by x plus 1 ka whole square. Yeah. Now we'll just simplify. So what we'll get after simplification is we'll just multiply it by x plus 1 here, x plus 1 square here. So fx by x square plus 1 is equal to 1 by x square minus, this would cancel out and would leave us with fx by x square plus 1 by x square, I hope so. Oh no, minus 1 by x square. Yeah, so these two would simply cancel out. Oh sorry, I made a mistake here. Actually this would be 1 plus x ka whole square over here, and this can't get just cancelled out. So yeah, sorry for that. I'll rewrite it here again. This finally makes it into fx by x square plus 1 is equal to 1 plus x square by x square minus fx by x square minus 1. Okay, minus 1 by x square. So when we simplify this, open this up, it becomes 1 by x square plus 2 by x plus 1, and these cancel out, and all we are left with is fx by x square into 2 is equal to 2 by x. Now what this means is basically for all x n equal to 0 we have fx is equal to x in a simple term. We can go into more detail here, like we can substitute x less than 0, x greater than 0, but for all practical terms you can just simplify it to fx is equal to x. Now at x is equal to 0 we can simply substitute it into the first equation here, and we'll find f of 0 is equal to minus of f of 0, which means f of 0 is equal to 1. Hence the graph of this function would be continuous in all domains, and this would be an identity function. So yeah, that's it, hence proved. So we are now on a final problem, the final example problem, and here it is. Let fx is equal to x minus a1, x minus a2 to x minus an plus 1, where a1 to an are distinct integers. So they are distinct and they are integers, and then we have to show that if n is odd, then fx is irreducible over z, that is the integer range, and if n is even, then either fx is irreducible over z or it is a square of polynomial with integer coefficients. So let's go ahead, and first of all the important thing here is to assume that fx is no assumption, sorry, is to know what irreducible is. So irreducible is basically well, let's talk about reducible. So reducible would be fx could be factorized into px and qx. So if fx can be factorized like this, then it is reducible, and if it is not factorized, if it cannot be factorized like this, then it is irreducible. So we'll go ahead with that. Okay. Now we'll solve the first one, that is if n is odd, fx is irreducible over z. So fx has integer coefficients, like if they're actually 1, so we can safely assume that let n is equal to 2n plus 1. Okay, so standard odd number thing, and we'll assume that fx can be factorized like px and qx. So fx would be px and qx. Now all we need to show that this is not possible, and we are going to do it like, first of all what we see here is px. Let's take a px, alright. Now px can have values, and one more thing, let's put in all values I. Let's take a number I between 1 and n, okay, and we'll put it into this equation. So for each value of I is equal to I between 1 and n, including 1 and n, then px into qx would be equal to 1. That means p xi pqi, or let's just write it this way, p of ai into q of ai is equal to 1, and this stands for all n values, or n is equal to 2n plus 1 values, correct? That means PAI should be should have and one more thing, P and Q have integer coefficients, remember. So PAI should at least have m plus 1 roots that are either 1 or m plus 1, at least m plus 1 roots, or that are either minus 1. You see, because it has to yield a value of 1 and it has only integer coefficients. So it has to have at least m plus 1 roots that are either 1 or minus 1. Like, say for example, it could have, let's say n was 11. So it could have 8 roots that were 1 and 3 roots that were minus 1. So in any case, each of these are greater than each of these is greater than m plus 1, where m is equal to 5. So each of these is greater than 6. Hence, what we need to prove is PAI cannot have so many roots. Now, one more thing. We'll have to assess the coefficients. We'll have to assess the degree of these. So, one more thing in reducibility. The degree of these functions px and qx, let's assume they are r and s. R and s are natural numbers here. Each r and s should be less than n individually. Hence, r and s, r plus s should be less than equal to 2n plus 1 here in this case. That means r and s cannot both be greater than m plus 1, sorry. Like say we put both of them m plus 1 here, then we'll yield 2m plus 2. So it's impossible for each of them to be greater than m plus 1. But what we just found above was that P of AI has greater than roots which are P of AI is equal to 1 for more than m plus 1 values. Correct? That means it has more than m plus 1 roots, like PAI minus 1 has more than m plus 1 roots. But what we just found that R should be less than equal to m plus 1. Like it can have maximum value of m plus 1. Yeah. Okay. So we found that R needs to be less than m plus 1 here. But what we found here is that PAI minus 1 should have more than m plus 1 roots. Hence this is contradictory, because if PA minus 1 has more than m plus 1 roots, but the degree of the polynomial is less than m plus 1, hence it must be a constant polynomial, which is contradictory, because again both of them, like px and qx, are interchangeable. Both of them cannot be constant because fx has a degree of n. So yeah, like this is contradictory, and hence fx is irreducible. Yeah, so that's the first part. Now we'll jump to the second part. Okay. So I made a little mistake in the previous part. That is, I assumed that r is less than equal to m plus 1. Well, the statement here says that r plus s is less than equal to 2m plus 1. Hence, both r and s cannot be greater than m. That means one of them can be m plus 1 and the other can be m. So the right statement to use here would be r less than equal to m. So yeah, and one more thing, since px and qx are interchangeable, so we can assume any one of them, and when we assume r less than equal to m, then we see that PAI has more roots than m. That is, it has at least m plus 1 roots. Hence the statement would be contradictory and it is not possible. Now when we go to even, let's say n is equal to 2m. Now in this case PAI into QAI is equal to 1 and I is equal to 1 to 2m. right? Yeah, 1 to 2m. So that means PAI has to be either 1 or minus 1 for at least m plus 1 values. Sorry, for at least m values, right? That means it has to have at least m roots. Yeah, so it helps when you write this out so you don't get confused. So just like in the last part here, we said that PAI minus 1 should have more than m plus 1 roots, but R should be less than m. This same thing would be applied here as well, where we can safely say that R needs to be less than equal to m. Hence, what this means is if R less than m, like there are two cases here. If R is less than m, then this statement will not hold. Like both of these would not hold. The first statement being this, first statement being this, and the second being this. So Px has to have at least m roots, but R is less than m. Hence, Px has to be a constant function, which is again a contradiction. So fx would be irreducible in that case. But when R becomes equal to m, like the third case here, then 1 and 3 can go together hand in hand. That means Px has at least m roots, and Px degree is also m. That means Px is a polynomial with degree n. With degree r is equal to m. So now to prove that they are a perfect square, like Px is equal to Qx, we'll see that Fx here has a coefficient of the coefficient of largest power of x is 1 actually. Hence the coefficient of largest power of x in Px and the coefficient of largest power of x in Qx should also be either 1 or minus 1. What that means is the polynomial Px minus Qx should have a degree which is less than m. Right? That is because both of them have the same degree, like r is equal to m is equal to s. So, and both of them have the coefficient of highest power of x to be either 1 or minus 1. Like both of them should have same. Hence, when we subtract them both, then the degree of the polynomial should be less than m. Now, what we see here is something opposite. Like, yeah. Let's say we put in all values of I over here, right? Like PAI minus QAI, right? So these are all 2m values of I. But according to the statement given in the question, like what we assumed was that PAI into QAI yields a value of plus 1. So PAI is equal to QAI, that means. And this statement holds for each value of I, like from 1 to 2m. Correct? That means we just, so what that means is PAI minus QAI is equal to 0. has 1 to 2m roots, but we just found here that it needs to have, the thing is px minus qx would be a polynomial of degree less than m. Well, these statements seem to be contradictory, but they can only be satisfied when px is exactly equal to qx, right? That way px minus qx would have a degree less than m, that is 0, but pai minus qi is equal to 0 would have again infinite roots. But this statement would be only satisfied when px is equal to qx. Hence, both of them need to be a perfect square. That is proved, I guess. Yeah, and since px and qx both have integer coefficients, hence the statement is proved. Thank you. So yeah, that was all about functional equations. Like, we've covered all the essential examples. You should go ahead and solve the exercise number 2.3, and yeah, that's it. Exercise makes a man perfect.